do the problems for you. I have all the answers here. I'm going to explain them one by one, though, pretty quickly. Okay, so the first question, increasing the temperature increases the rate of reaction by, and the answer is D. Increasing temperature in no way lowers your activation energy, so A is wrong. B, increasing the no, nothing to do with activation energy. Lowering the frequency of effective collisions. Well, that would have the exact opposite result. That would lower the rate of reaction. So D is the correct answer. It increases the frequency of your collisions. All right, 2. A catalyst is added to a system at equilibrium. If the temperature remains constant, the activation energy of the forward reaction it decreases. That's why a catalyst is so useful. It lowers your activation energy, and it makes it much more quick because that hill, that hump, that barrier you have to get over in order to start the reaction is lowered. So if you imagine yourself walking over a big hill or a little hill, the little hill is much easier to get over and you walk over it more quickly. Okay? 3. After being ignited in a Bunsen burner flame, a piece of magnesium ribbon burns brightly, giving off heat and light. In this situation, the Bunsen burner flame provides, a magnesium ribbon doesn't start burning until it's provided with the energy from that flame. So if it can't get going without that initial bump in energy, right, that bump in energy, that little hump that it needs to get over, that it's being provided with, that energy, that's your activation energy. So that flame provides the magnesium with the activation energy necessary for the reaction to occur. Okay, and that's the case with a lot of reactions that require fire to get started. All right, 4. In a reaction, 5 grams of powdered iron will react faster than 1 gram of solid iron because powdered iron B has more surface area. Remember, the more surface area it has, the more locations that it is able to react with, and therefore it's going to react a lot faster. 5. Which statement correctly describes an endothermic chemical reaction? All right, so if you draw it out, and actually this shows it really nicely, so I'm going to show it here. This is an endothermic graph. Your products have a higher energy than your reactants, and your delta H is positive, so B is the correct answer. For 6, guys, I just answered that question. That's 2. 2 is endothermic. 1 would be exothermic. These, I have no idea what they are. They just threw them in there, so don't get tricked by that. These are 2 graphs. These are bogus. They don't exist. Those would not be reactions. Okay? Alrighty. 7. What is shown by letter A? So letter A, if you notice, here is my reactants, and reactant energy would be from here all the way down to the bottom. My product energy would be here all the way to the bottom. So if I take here all the way down to the bottom minus here all the way to the bottom, if you notice, what that will get me is just A. Okay, so all of that minus just C, that gives me just A. So the difference between the reactants and the products, that would be the heat of reaction. Okay, so the answer is D. What is shown by letter B? Remember, here my reactants, they've got to get up over this hill. B is the activation energy of the forward reaction because I'm going in the forward direction. Remember, if I include a catalyst, if you watch my arrow, that is what will happen to the activation energy, so B will be affected by a catalyst. What is shown by letter C? Well, C is showing if you go from your products, you go backwards, up and over, that vertical distance from here to here, that's the activation energy of the reverse reaction, to go from your products up and over, okay? Because your products already have this amount of energy. All right. For 10, for an exothermic reaction, what does the activation energy of the reverse reaction equal? Notice, I drew this out. So I first drew an exothermic graph, okay, and it says, what does the activation energy of the reverse equal? So here's that energy. I didn't draw an arrow, I just drew my squiggly lines, okay? And notice the activation energy of my forward reaction, this amount. This is my activation of my forward, so it would be this, plus the activation energy, sorry, not the activation energy, plus the heat of reaction, right, the difference between my reactants and my products, this difference right here, which is represented by this plus this equals my activation energy of my reverse, which is exactly what D is explaining. So take a look at that, make sure you understand it, but D is the correct answer. All right, for 11, the equilibrium constant for the reaction. Remember, it's the concentration of one of your products raised to its coefficient times another product, if you have another one, raised to its coefficient, all over the reactants raised to their coefficient, so on and so forth. So here, it would be the concentration of HI, so you put it in brackets to represent concentration, raised to the second power, so squared, divided by H2, well it's not, doesn't have a coefficient, so it's not raised to anything, times I2, so that's best represented by A. Alright, for 12, an equilibrium mixture of SO, and it gives me all that information. I don't care about temperature, don't let me mess you up. I write out, and I would really like for you guys to write out your equilibrium expression first. So my K, or my KEQ, equals, here's my reaction right here, so O2 times SO2 squared, because those are my products, all over SO3 squared. Now, I'm going to plug in my values. I know the concentration of O2 is 0.59. I know the concentration of SO2 is 0.03, and of SO3 is 0.41. So I plug in all those numbers, 0.59 times 0.03 squared, divided by 0.41 squared. I get 0.0036. If I put that into scientific notation by moving the decimal place over 1, 2, 3 places to the right to make it a bigger number, it would be 3.6 times 10 to the negative third. That's my answer. That's B, which is down here, which is on the same page for you guys. All right, next problem, 13. Another reaction coordinate. Sorry, guys, there are going to be a number of them, so get comfortable with them. We're going to use this diagram. It says which arrow best represents the forward activation energy. Remember, to go from reactants, I've got to get over that first hurdle. That vertical distance is represented by 2 right there. Okay? So B is your answer. Using the diagram above, arrow 3 best represents, okay, so here are my products, here are my reactants. Notice this is representing the distance between the energy of my products and my reactants. That is the definition of your heat of reaction. So the answer is D. According to the diagram above, which arrow represents the part of the reaction most likely to be affected by the catalyst? Remember, that's going to be your activation energy. Okay, so that's going to be the catalyst is going to make the activation energy much shorter. Notice it only provides the forward activation energy, not the reverse, so you can't put both as an answer. So 2 would be your answer. If there were a 5 for here, that would also be affected by your catalyst. Alrighty, for 16, okay, I give you your KEQ now. I give you a couple of concentrations, but then I ask for the concentration of NO. So I would highly, highly, highly recommend, and I stress this, guys, putting all of that formula out there, right? Writing your equilibrium expression. So KEQ equals NO squared, because that's your product, right? NO, concentration of NO squared, because that's your coefficient, all over N2 plus O2. Now, I know KEQ, it's 1.0 times 10 to the negative fifth. That equals NO squared, because I don't know that concentration, all over 0.6 times 0.6. I'm going to cross multiply, so 1.0 times 10 to the negative fifth times 0.6 times 0.6 equals NO squared. Now, to get rid of this squared, I need to square root both sides, and when I do that, I get 0.0019. I need to put that into scientific notation, so I move the decimal place over 1, 2, 3 places, and I get 1.9 times 10 to the negative third. That's B. I would need to see all of this work, guys, to give you credit, so make sure you're comfortable with that. All right, 17. When extra NH3 is added to the following system, what happens? If I increase NH3, guys, it's going to shift to the left. All right, so the answer is B. When H2 is removed, I decrease H2, then it's going to shift to the left to make up for that loss, so it's B again. 19. Consider the following reaction. Okay, Le Chatelier's principle predicts that adding O2, so if I add O2, it's gonna cause me to shift to the left, all right, in order to restore that equilibrium. Le Chatelier's principle, same reaction again, predicts that increasing the pressure. Now I have to know how many moles of gas I have. On this side, since they are all gases, I can make that assumption that it will cause a shift. I've got 2 moles of gas here. I've got 3 moles of gas here, because this is 2 plus 1 is 3. So since I'm increasing the pressure, it's going to shift in the direction that towards the fewest number of moles, which is 2, so it's going to shift to the left. So the answer is B again. Now, this is asking me the effect that of increasing heat. Okay, notice your delta H is positive, therefore your delta H should be on the left-hand side because it is being absorbed, it's being consumed, it's not being released, which would be the case for exothermic. So if I increase temperature now, if that goes up, then it's going to cause a shift to the right. So the answer is A. 22. If CO is removed from the reaction, the system will shift. Now, if I decrease CO, therefore it's going to shift to the left. That should be pretty easy at this point. Given this reaction, and that is exothermic, in order to increase the concentration of Cl2, what would I need to do? Now, notice I'm not saying, right? I'm not saying if I increase Cl2, what shift will occur. I'm saying what direction would it need to shift in order to increase Cl2, right? So, yes, if I increase Cl2, it would shift to the left, but no, I'm saying to increase Cl2, in what direction would I want to shift? And that is to the right, because if it shifts, and I can't express this, I don't have my hands, unfortunately, watch my cursor. If it shifts to the right, I'm forcing PCl3 to become P and Cl2. So I'm increasing not only Cl2, but also P by shifting it to the right. Okay, now notice 23A is linked to 23B. In order for the shift in 23A to occur, the heat should be, now I want to shift to the right, therefore in order to shift to the right, what do I need to do to the heat? Well, delta H is on the right hand side because it's exothermic, I put that in there. In order to have that shift to the right, I would need to decrease delta H, I would need to decrease the heat. Treat delta H just like another compound. You can even cross it out and put H2O. I don't care. If you decrease H2O, for example, or any other compound, it would shift to make up for that loss. Same with heat. If you decrease heat, it's going to shift to the right, which we want, okay, in order to make up for that loss. So therefore, you would want a decrease in heat to cause a shift to the right. And those are all the problems, guys. So go back if you didn't understand anything that I was talking about, or if I said it too quickly. And if you have questions, shoot me an email, and hopefully I'll have internet access this weekend.